So I start today the fourth lecture, and I will change the topic with respect to the three first one, which were devoted to the introduction of cavity QED experiment in relation to the experiment we perform in my lab at Laboratoire Kastler-Bruxelles to demonstrate some feature of quantum theory of measurement. So I will not tell much about quantum theory of measurement here. I will rather try to make kind of overview of the development of the field of quantum simulation using a system close to what I like, Rydberg atoms. So I will tell you about quantum simulation with neutral atom trapped in optical tweezer and interacting, talking to each other using a dipole-dipole interaction between Rydberg atoms. So if you want to download the slides, I have put them there. I've not sent them yet to the organizer, but you can download this directly right now. It's okay? Okay, so let's start and motivate a little bit this idea of quantum simulation, which become very popular in the field of quantum technology. And as it is easier as quantum computation, I think that's already a very active topic, and it will remain a very active topic for quantum technology for a while. So what is the idea? The idea is that if you want to simulate the behavior of a quantum system, if you want to understand a quantum system, you have one way is to do some experiment and measurement. Another way for understanding it is to numerically simulate the problem with a classical computer. But for getting some quantum feature, and I will come back about that a bit later, Feynman suggested that the best is to use a quantum computer or a quantum simulator. So it means that the idea is to build kind of artificial system, which is a quantum system, behaving in a similar way as the system you want to simulate. And then you can ask, what do you win while doing that? Indeed, the idea is what you win is that the artificial system eventually provides you more flexibility as the real one. And for example, if we think about simulated, what happened into a piece of matter or in a metallic conductor. So you never access to some observable of the system with real material, like the position and correlation between individual electrons. So if you build a quantum simulator of spin system, you will be able to eventually access to individual state, to individual measurement of every single particle, and then access any kind of correlations in the system. So that's one example and one interesting feature of quantum system. So the kind of thing of observables that you can access, which are eventually not accessible in the real material. The second interesting feature is that the artificial system can be so well controlled that you can vary the parameters of the Hamiltonian in a way that is not accessible with real material. So basically, in a material, if you want to change parameter, you eventually have to build a new piece of material and fabricate it a little bit differently, which is possible but kind of constrained. If you have kind of a simulator where all the parameters of your Hamiltonian are tunable with external fields, and I will give you example in the case of Rydberg atom-based quantum simulator, then you can even go in some field where normal material does not go. Then it can give you idea to discover new phenomena, and then you can have a kind of back action which consists in trying to fabricate real material close to what you think is interesting from your simulation. So that's the general framework of quantum simulation. it, in principle, allows you, by building what I would call artificial matter, to have a very deep understanding of the details of the physics, and eventually to operate quantum mechanics in some fields where, or in some parameter range where it was not yet operated. So, and let me give you an example of such a system, which is indeed difficult to simulate just numerically in order to illustrate the power of quantum simulation. So let's start with the simplest possible quantum system, a two-level system, a single spin. So for a single spin, all of you knows to calculate any Hamiltonian evolution, calculate all observable, and there is not much mystery. If you take 3 spins, the Hilbert space is a little bit bigger, but you manage to do it as well very easily with a very small computer. Then if you consider many spins, and many is not much, like 40, 50 spins, then you cannot anymore simulate it with neither your laptop computer nor the biggest computer you can find on the Earth. And the reason for that is the size of the Hilbert space of such a system, which grows exponentially as a function of number of spin. And so it's kind of abstract, but you can remember of this Chinese guy who asked as a reward for something to have 1 grain of rice on the checkerboard, and then on the second one, 2 grains. And so people thought that it's ridiculous to make this only 64 times, but in the end, the number of grains were more than exist in the whole world. So here, if I can give a figure, if you take 40 qubits, 2 to the 40 qubit is like the number of atoms in the universe. So if you want to encode physically the information, which is the probability amplitude corresponding to each of the coefficients of this huge state vector in the huge Hilbert space, you only have 1 atom to encode 1 C number. So you see the limit. It's exponential are really huge things. So then it means that when dealing with larger system, doing quantum simulation is at some point the only option, except, of course, if you want to understand this doing approximation. But to validate approximation, it's very interesting to have a real physical system simulating your Hamiltonian. So that's the general context. And then what kind of Hamiltonian can be considered with spin? Indeed, the Rydberg atom simulator I will talk about are most of the time simulating spin Hamiltonian. And so I have depicted here the 2 typical Hamiltonian which are combined in this experiment, which is a so-called Ising Hamiltonian, which corresponds in terms of Pauli matrices corresponding to the spin, individual spin 1/2 system. The interaction here is written as a product of 2 sigma z components with a coupling strength that I will call here GZ. So physically, it means that if I take 2 spin, the energy difference between spin up and spin down for the second spin depends whether the first one is up or down. And that's this kind of interaction is called the Ising Hamiltonian. So the other very famous Hamiltonian regarding spin is the so-called XY or flip-flop Hamiltonian or Heisenberg Hamiltonian, which written like this in terms of the sigma x and sigma y Pauli operator, and which can equivalently be written in terms of sigma plus sigma minus for spin 1 and spin 2, plus sigma minus sigma plus. It's an equivalent writing. And so it's called flip-flop Hamiltonian because if you start with one spin up and the other spin down, the evolution related to the Hamiltonian is an exchange of the excitation between the 2 spins. So as a function of time, the first spin will go down while the second one will go up and so up. And that's the so-called flip-flop interaction. So why are there already, there's very simple Hamiltonian already interesting? indeed, they lead very rapidly when you go in 1D or 2D to interesting open questions, and that are related to, for example, a property of spin, which is that if you have a triangular lattice geometry, you have a phenomenon called frustration, which means that, okay, if I put this spin up and this spin down and have antiferromagnetic interaction, how do I put this one so that I minimize the energy, and how to find the ground state if I am not just considering 3 spins, but a few tenths of spin. So the physics of frustrated magnetic system is complicated, and even finding the ground state in 2 dimensions is not an easy task. The other large family of phenomena which are not within the reach, or not easily within the reach of classical computation, is the dynamic of the system after a quench. For a system, even if you know very well the ground states, in many cases using some numerical approximation, it's much more difficult to look at dynamics because usually it involves a lot of excited states, and then the size of the space that you have to consider grows very fast. And then to describe how propagate the correlation in the system after a quench is an important system which is open in many physical situations. Another interesting situation is the investigation about the role of a disorder in a many-body system, and that's the physics of localization or many-body localization. So that's the side of fundamental physics for motivating quantum simulations. Indeed, there are also interests more related to the topic of what I would call the quantum information tasks, which are to give answer to optimization problem. Indeed, a spin Hamiltonian with tunable parameter can be shown to allow to solve a large family of optimization problem, like the problem to optimize the way to distribute electricity in a complex network. And that's problems which are numerically difficult for a classical computation. And also, of course, quantum computation is very close to quantum simulation with spin, because spin 1/2 are not only physical systems, but they carry 1 qubit of information, so they can be considered as qubit. And you will see that most of the tools developed for quantum simulation are also useful for quantum computation, to build quantum gates, and that's the same physics and the same basic elements that have to be combined. Indeed, I will not focus on the quantum computation aspect, because first, I'm not an expert of quantum computation, and indeed, from my experimentalist point of view, quantum simulation is much easier, even if not easy, than quantum computation. So I think with the present state of technology, we can already do a lot of interesting physics, even if we don't reach the threshold for having a fault-tolerant quantum computation, which is kind of a dream that nobody knows whether it will become or not a reality one day. So to complete this remark about quantum computing, indeed, I would like to mention the even deeper analogy between analog quantum simulation and digital approach related to quantum computing. Indeed, the two approaches are very similar. If you decompose, indeed, the analog evolution under the effect of some Hamiltonian, indeed, it has been shown that any Hamiltonian evolution can be split and decomposed in a succession of elementary quantum gates. That's a game which is called trotterization. So you can have in mind that everything which can be done in a quantum simulator could also be done with a universal quantum computer. But as we do not yet have at hand a quantum computer, we rather consider quantum simulation. Also, quantum computing is doing really huge progresses in the field of neutral atom in optical tweezer interacting by Rydberg interaction. So I will not come back to this, but I would like to mention this very impressive result obtained in the group of Michel Brune in Harvard, where they manipulate hundreds of qubits in the experiment. They move them to perform gate between part of the qubits and other part of the qubit. And in the end, they manage, for example, to implement some error correcting codes named color codes. And indeed, they were able to manipulate up to 48 logical qubits in this. Logical qubit means that it's already composite qubits that are made of several physical qubits in order to implement error corrections. So presently, it's not fully corrected for everything. It's not yet efficient enough so that you break the threshold for fault-tolerant quantum computation, but it's really already impressive progress. So then, how to simulate a spin system? I would like also to mention that there are many different physical systems which are well suited for doing quantum simulation, even if I will focus on a single one. So I would like to mention, of course, the superconducting circuit approach, which is run now by big companies like Microsoft, IBM, Google, and so on. So you heard about that, and there is a lot of hype around that. Then the trapped ions, I think, were one of the systems which was the first to develop the tools for quantum computation and simulation by having, before the other system made of a few tens to maybe 40, 50 ions. Now it's more difficult to break this limit and to go further, but I think they will still progress and find way to combine the larger system. Polar molecules in optical lattice, ultra-cold atoms in optical lattice. Of course, you can consider all the system as carrier of spin 1/2 information, so they are equivalent to qubits. Spintronics, when you can try to manipulate the spin of single electrons and then couple single electrons to perform quantum gates. So even if it's extremely difficult because it's kind of system where decoherence goes really fast in the solid-state system, I think there are a lot of efforts also in this direction. You can use atom in cavities. I will not talk about this anymore. And you can use the Rydberg atoms, not in free space, but by preparing them from a system of neutral atom in optical tweezers. So here is a kind of overview of the program of the course. And here I have written 2 timelines which are running in parallel. The lower one corresponds to the technical development which were key for the development of the field, which is basically the physics of optical tweezers for preparing single atom per tweezer for the experiment. And the upper line is a list, of course it's not exhaustive list, but of the most prominent papers about the physics of the systems once you get better and better way to control the atom in the tweezer, to increase the number of atoms, to have exactly 1 atom per tweezer. So the 2 things run in parallel. And the amazing thing is, I think that both stories more or less started at the same time, 2001, were 2 very important achievements. I think that not only the physics of quantum simulation, but also quantum, the physical implementation of quantum simulation and quantum computing idea was strongly based on an extremely nice idea by Lukin and Zoller in 2001. We introduces the concept of dipole blockade and show that one can take advantage of this to implement a quantum gate. And that's still this kind of quantum gates that are used, for example, in the Lukin experiment with technical improvement. But the basic idea was already there. And then at the same time, on the point of view of manipulation of a single neutron atom, the story really started in 2001, even if it was starting much earlier with single ions. But for the single atom, the story started in 2001 in the laboratoire of Philippe Grangier at Institut d'Optique in the south of Paris, where he demonstrated for the first time that single atom can be trapped in optical tweezers in the so-called collisional blockade regime. And this collisional blockade regime, I will go into the details later, corresponds to the fact that if your tweezer is small enough, and if you put it in a molasses, then you have some probability to have one atom in the tweezer, but you never get two. And so you only have 0 or 1. And the fact that you never get two is a key thing, so that you can then make complicated things with these single atoms in tweezers. So, and then I will present you the developments that I do not comment just now, but will comment this step by step. So you see that both stories are long, and do not hesitate again to interrupt me. It's not a big problem if I skip one of these papers. I prefer that really you get what I say. So stop me when too fast or when any kind of question. So to complete this, I would like also to stress that in the field of neutral atom quantum simulation and quantum computing, there are now very advanced startup companies. So the field goes out of the lab. And so I mentioned here the two main ones. One Quera from the Harvard, which emerged from the Harvard group, and one Pasquale, which is in France, and which emerged from the Institut d'Optique group of Antoine Brouwers. So you can see the timeline proposed by this. So I'm not sure everything is realistic, but there are really running efforts and developing means which are not anymore at the scale of a laboratory like mine. I think that the fact that they develop technically such advanced machines have a strong impact on what can be done and what will be done in the lab in the future. So in the first part, I will talk about the basic toolbox for this kind of experiments, which basically combine single atom in optical tweezers and interaction between Rydberg atoms. So I will first start with these two elements. So single atom in optical tweezer. So again, the timeline, and we start, of course, with the beginning. What is this collisional blockade which allows one to get exactly, or to get 0 or 1 atom in a tweezer, but never 2? Okay, oops, too many clicks. Okay, okay, no, it's not this one. Okay. So the idea of the collisional blockade is depicted on this scheme. So you assume that you already prepare an optical tweezer, which means that you have a laser beam, you have a high numerical aperture objective, so that you focus the beam in the focal planes of the system with a dimension of the spots which is diffraction limited. And when you have high numerical aperture, typically the size of the spot is 1 micrometer. So then you start with cold atom around the tweezer, and you look at the way the atom will fall in the tweezer as a result of laser cooling. So when the atom goes inside the tweezer, it gets light shifted by the tweezer, but if light shift is not too large, it still continues to be cooled in the tweezer. And if a single atom rises close enough to the tweezer, it falls down there, and it's cooled down to a temperature of a few 10 microkelvin. So that's a simple story. A single atom just falls at the bottom of the potential with friction, and then it remains there due to laser cooling. Let us now consider a pair of atoms. And if a pair of atoms gets at the same time in the tweezer, then when they get close to each other, they start to interact with each other. And if both atoms are in the ground states, then you have a weak attractive potential, which is a so-called van der Waals potential. So they get a little bit attracted, but not much happens. On the other hand, if atoms enter the trap while the laser, the cooling laser, is on, then another story happens, is that as a first step, one of the two atoms may be excited to the p level. We consider alkali atoms where the transition, the resonance line is between S and p level. For rubidium, it's 5s and 5p level. So let's consider a pair of S plus p. Then they interact, but interaction is much stronger, because if you have two different Rydberg levels, they do not interact just by the van der Waals interaction, which is second order with respect to dipole-dipole Hamiltonian. They interact to first order. And indeed, that's related to the fact that the SP and PS quantum states are two states which are degenerate, coupled to first order. They repel each other. And there is one very attractive branch with here potential varying as 1/R3. And then the atoms start to accelerate. They want to collide to each other due to this strong dipole-dipole interaction. But of course, this does not last too much time because the p level does not have infinite lifetime. So after typically one lifetime of p level, which is 25 nanoseconds for rubidium, the atom stops being accelerated. They emit a photon. And indeed, they gain a kinetic energy, which is delta E. And if you put the number, this delta E is much more than the depth of the trap. So both atoms get such a kinetic energy that they are lost and they are expelled from the trap. So the trap, together with the cooling laser, acts as a kind of filtering system which only authorizes to have either 0 or 1 atom in the trap, but never 2. And of course, if 2 is forbidden, 3, 4, 5 are also forbidden. Indeed, this has to do with the dynamic of the loss, the two-body loss rate, with respect to the loading rate of the trap. Of course, if you load too much, you will break this. But this was indeed investigated in details in the group of Philippe Grangier, especially in this paper by Nicolas Schlosser, who performed his PhD of that. And so they made a model of what happened as a function of the loading rate. So you make a mod with a stronger and stronger source of cold atoms. And here is the average number of atoms in the trap, in log scale, both log scale. And you see that if the trap is large, like 11 micrometer, which is not so large, but 10 times larger than the diffraction limited spot I talked about before, then when you increase loading, the slope changes at some point, but basically you continuously go to hundreds or thousands of atoms in the trap. And that's the regime people are using when they put a lot of atoms in the dipole trap. Usually the dipole trap are large enough so that the atoms have a lot of room and do not collide so much. So two-body losses are responsible of this change of slope, but they do not lead to collisional blockade. So if you decrease the size of the trap, you see then you go to the green curve, which looks a little bit like a S shape. And then for a 1 or fraction of micrometer trap, you have a nice plateau of the number of atoms, which is an average in log scale here. This is 1/2, 50% locked-in probability. And that's the signature of the collisional blockade regime. And you see that it is very robust. Here, it's robust over more than 2 orders of magnitude on the loading rate. So, which means that in the experiment, it's not so difficult to go into the collisional blockade regime. As soon as you have a tweezer, you have a MOT, you do not even need a molas. Basically, you always have enough atom to load the tweezers. And to have too much, you really need to have a lot. So you are very easy in this, and this works very well. And then you can experimentally check that this process actually works. And to check that, you make the imaging of the fluorescence light from the atoms. And this imaging gives you spot at the position of the tweezer. And if you make the statistic of the number of photons you detect for a given spot, you get, indeed, for without loading for 0 atom, you get a single peak, which is the background light for an empty tweezer. And if you start loading with your mod, you see a second ping appearing corresponding to the presence of 1 atom in the tweezer. And typically, the number of scattered photons you detect is like 100 to a few hundred. So you have usually a very good contrast between the 1 atom peak and the 0 atom peak, which means that the error of your measurement is weak. And typically, presently, in the best experiment, the error rate is below 1% and go down to 1 per 1,000. The amazing thing is the total suppression of the 2 atom fluorescence peak, which shows a rise around there at twice the number of photons you scatter with a single atom. And so you can make a quantitative analysis of that, and the result is that the 2 atom imperfection in this experiment can be completely negligible. They are below 10 to the minus 3. Indeed, I never got a number about this because all other imperfections come before. So that's very nice. You have either 0 or 1 atom in your tweezer, and that's the way all experiments with optical tweezer start presently with this dipole collisional blockade process. So this does not want to work. I think the battery is off. I will take I have another one. Okay. So that's the Hertz single tweezer, 0 or 1 atom. So let's go one step further by doing not single tweezer, but many tweezers. And the story developed very much in 2014 with what I call the SLM area, where indeed people start to generate arbitrary arrays of atoms in 2-dimensional geometry and with up to 100 traps in the array. And indeed, here is the way it works. Indeed, the story started even before 2014. The first experiment in the group of Philippe Grangier with SLM was generating 3 traps and 3 atoms in the trap. But then the technology of using SLM for generating a large number of traps developed. And basically, the principle of the SLM setup is depicted here. So here you have 2 high numerical aperture, either aspherical lenses. Historically, it was more a complex objective with high numerical aperture, which focuses an initially collimated beam into spots forming tweezers. So you have a camera for looking at the fluorescence of the atom, either directly, for the fluorescence, we look at the backscattered light with some dichroic mirror. And then the trapping laser is 850 nanometer. For rubidium, it's red detuned with respect to the resonance line of rubidium at 780 nanometers. And indeed, a collimated beam hits SLM, which is a phase modulator of the wavefront. And indeed, it can be shown that if you have a phase, spatial phase modulation facility of an incident plane wavefront, by using a so-called Gershberg-Saxton algorithm, which is not now universally used for people generating arrays for optical tweezer, you can indeed engineer the modulation, the phase modulation here on the SLM, so that in the focal planes on the lens, you generate arbitrary patterns of spot. So I will not tell you about the details of the cooking one have to do in order to calculate the phase mask you have on the SLN. The thing is well known and described, especially in this paper, by D. Leonardo. And the idea is that you start with the first guess for what should be your wavefront, and the first guess is driven by physics. You say that to have a spot at a given position, you have to put a plane wave incident on the lens with some angle, with some incidence direction, because the position of the spot is proportional to the angle between the k vector of the incident wave and the axis of the lens. And so for each spot, you take a plane wave, and then you use as a guess, indeed, for the phase, a sum of some coefficient, C over P, and plane wave, E, Kp, scalar R, where R is a position on SLM. And indeed, that's an amplitude, the sum of this plane wave. If you Fourier transform it by using Fourier optics, it gives you the desired array of spots. The difficulty is that you cannot generate this directly with the SLM, which allows you to control the phase of the incident field, but not the amplitude. And if we look at this, the modulus of this is different than constant. So this you cannot do rigorously, but you do an approximation. Instead of having this, you divide. So we remove that, and you divide that by the norm of the same thing. And this, by construction, have a unit norm, so it's uniform, and so it corresponds physically to uniform probability. And then when you make the Fourier transform of that, it's not exactly the array of spots you want, but it already looks pretty much like this. Basically, you still have the Fourier component you want in your phase mask, which means that you will have light at the desired position, but you will also have parasitic spots at other positions due to the difference between the exact solution and the normalized one. And then the kind of magic trick, because now I think there is no proof of convergence, is that if you start like this, you make the Fourier transform, then you change, you tip the phase of the Fourier transform, but you replace the amplitude by your target. You go back by inverse Fourier transform in the plane of the SLM, and you repeat that. In the end, you converge with a very good approximation to what you want. Indeed, what does the algorithm, and this is explained in this Di Leonardo paper, it maximizes the energy in the tweezers with respect to the parasitic spots that you don't want to have. So it works very well, up to thousands or 10,000s of spots. So it's really a very efficient thing. And it was first implemented with a more restricted number of atoms, of tweezers, with about 50 to 100 tweezers. So in this 2014 paper, they demonstrated the ability to load, to generate this arbitrary array, but indeed the method was already known. What they demonstrated is that they can efficiently load atoms in there. And here you have average images of atoms loaded in this tweezer. 3 years later, they also demonstrated that you can not only generate tweezers in 2D, but also in 3D. The idea was already also in this Di Leonardo paper. And the idea is that for each K component of your guess, your starting function, you add an additional phase factor corresponding to the phase generated by the Fresnel lens, which generates a spot just shifted in the Z direction. And so by combining a sum of K vector together with some length, with some focal length, you can generate these two three-dimensional patterns. And as this was generated in France, they find it fun to generate a 3D Eiffel Tower. So the point is that this is very nice, but it's not yet what we need, because here the loading benefits from collisional blockade, but it's not yet deterministic. You have statistically either 0 or 1 atom in each tweezer, And these images are not single-shot tweezer, single-shot image. If you do a single-shot image, what you observe is that some spots are empty, some are filled with a ratio of 50%. So you have to do something more in order to get rid of the randomness of loading. And the trick they played to get more was played in 2016, when for the first time arrays of up to about 50 atoms were assembled without defect. So which means with exactly 1 atom per tweezer. And it was more or less simultaneously implemented in the group of Antoine Brouwers and Michel Brune. So how does it work? So the principle is depicted here. So in the experiment, in addition to the SLM, an additional tool is added, which is a 2-dimensional acousto-optic deflector. So acousto-optic modulator are used to shift the frequency of the atom, but they also shift the direction of the diffracted light. But if you switch from AOM to AOD, indeed, it's the same kind of thing, except that the material is different, the velocity of sound is different, and the diffraction angle is much larger. So if you want to have large deviation, rather by AOD than AOM. So it's 3-dimensional. Indeed, 2-dimensional means that you have 2 crossed acousto-optic modulators so that you can move your spot in 2 dimensions. And so the parallel beam, the collimated beam generated after the AOM is also focused, is overlapped with the SLM beam and is focused on the atomic sample in the same way. And then, as you have AOD, you can decide to put your moving tweezer light at a site where there is 1 atom. And the idea is that if there is 1 atom somewhere, you can move it to another site deterministically. And how to move it? For example, first image tells you like this, that there is 1 atom here, but of course you want to have this array which is smaller, but there is no defect at the center. So the idea is to move this atom from this side to an empty side of the middle, avoiding the others. And this can be done by a moving tweezer that you switch on adiabatically at the position of this atom, and you switch it on with a power which is 10 times stronger than the initial tweezer. So that when it starts to move, the potential that moves is deep enough so that the atom will just ignore the initial position and will start to move with the moving tweezer. And once you get at the right position, you just do the opposite. You stop the movement, you adiabatically reduce the intensity of the moving tweezer, and the atom is here. And this is very efficient. At that time, I think efficiency was like the probability to lose the atom during motion was of the order of %. It can be much less if you really optimize the way you accelerate and decelerate the atom, and the effects are, again, much less than a %. So with this technique, indeed, now all experiments dealing with a single atom in optical tweezer use this algorithm to prepare the atom. Basically, the array you want to use is loaded randomly. You make it larger than the target array, and then you look at where there are atoms. And then, with the tweezer, 1 by 1, we move the atom to fill the inner part. And eventually, if you have too many atoms, you just throw away the ones that you don't want. And you get this nearly perfect filling lattices. So this is a single-shot image. So not an average, which means that basically errors are not there. The typical performance for a bit more than 200 atoms is like less than 3% of defect-free arrays, which were limited in the first experiment was by the lifetime, the collisional lifetime of atoms in the optical tweezer. It takes time to rearrange the atoms, and if you have a single collision during that time, you lose 1 atom. And so with 20-second lifetime error rate is like 3%, but now people can have a very good vacuum with the lifetime up to minutes or tens of minutes, and this limitation can be overcome. It's not easy, but it can be overcome. So then the next step in the control of the size of the tweezer was the implementation of this process, but in cryogenic environment. And you see that's the very big difference between the normal room temperature environment and the cryogenic environment is the lifetime of the atom in the trap, which is like 6,000 seconds instead of tenths of seconds. So why it is so good? Indeed, when you deal with a cryo, you have harder work, because I know very much that it's harder to operate cryo than UHV, but then you get the vacuum for free, because the cryo pumping of the 4K screen of the cryostat is so efficient that basically you have nothing left in your setup except a little bit of hydrogen that you can eventually pump with a cryo pump. So basically, vacuum is extremely good in cryogenic environment, and this allowed to a cryostat which was fabricated by a French company, My Cryofirm, and which was implemented in the group of Antoine Brouwers to prepare defect-free arrays containing up to 300 atoms, and in more recent versions that even reached 2,000 atoms in this kind of cryogenic environment. So you see that there were huge progress in that. And indeed, even more recently, another technique was invented to rearrange the atom, which is not indeed based on acoustic modulator. So this paper presented the result obtained by a Chinese group in Shanghai, where they demonstrated 2,000 atom defect-free arrays, which were generated moving the atom using the SLM itself. So for this, you need a fast SLM, but now the technology is good enough so that FLM are not as fast as AOD, but are fast enough, and they win because they can do the rearrangement in parallel for all the atoms. So basically, you have a SLM generating some array, you look where are the atoms, and then you switch the SLM so that you only keep the tweezers which are full, and then you recompress them by reprogramming the phase mask on the SLM. So this was very efficient, and I think this may be the future of rearrangement in this kind of experiment. So the second rearrangement principle I would like to also present is the one implemented in Michel Brune group in its first experiment dealing with 51 atoms, which was a 1D version of the rearrangement, so using only a 1D acoustic modulator, and in which basically you fabricate a line of about 100 tweezers, not by using the SLM to generate the tweezer, but by using a synthesizer which sends inside the acoustic deflector many different tones, many different frequencies. And each frequency corresponds to one spot in the focal plane of the lens, and this spot creates a tweeter. So you see that that's an alternative to the SLM method. You don't need SLM for that. You need just a good synthesizer generating at the same time many different frequencies. Indeed, they use arbitrary waveform generators that they program in the right way. And then, whilst they look at an image at the system, they know which tweezer is full and which is empty. They remove the tone corresponding to empty tweezer, and then they compact all the frequency spectrum so that all the full tweezers are become equidistant, and then they can start the quantum simulation. So of course you can make all the atoms close to each other, but you can group them by 2, by 3, or by more. It's kind of very flexible because you can, in 1D, arrange the geometry just by programming frequencies. Indeed, in 2D, it's generalized, but it's more constrained than the SLM. You cannot generate arbitrary arrays. So I think in 2D, SLM are still very interesting. So anyway, that's the way they proceed to perform this 1D preparation of a chain of 51 atoms at the same time as the French group did this in 2D with the moving tweezer. So then a word about the cryogenic achievement. So just to see you how nice is a picture. I think there are several difficulties when you go in a cryogenic environment. One difficulty when you want to go to very large number of tweezers is that if you use a symbol, as it was used before in the group of Antoine Brouès, if you single a spherical lens, you have aberration, which prevents you to have good tweezer in the side of the image. So from that time, we invented in my group a technique which allows to correct this at any position of the field, but it was not existing, this method at that time. Then they have to switch to use very expensive optimized lenses to put them in the setup, and using these very high numerical aperture lenses, they have a large enough field of view so that they can prepare up to 2,000 traps. And after rearrangement, they can manage to load up to 800 atoms in the cryogenic setup. Indeed, this experiment was not perfect because the vacuum in the cryo was not what it could be expected, but I think it can be still improved very much. And the record presently in terms of number of tweezers, but without rearrangement, because it's a challenge to rearrange really huge number of atoms, is an experiment performed with cesium in the group of Manuel Endres, where he managed to generate with the SLM up to 12,000 traps. And I think the difficult part for this is not the SLM. You just run Gerber-Saxton algorithm and you get the right array with the SLM. The limit becomes a technical limit which becomes strong is the total power you have for your trapping laser. And you typically need like 1 milliwatt per optical tweezer. And so if you have 10,000, you already need a 10-watt laser. And of course, you have also always a difference between the output power of the laser and what is in the experiment. So now people are running for having 30-watt or 100-watt lasers, continuous lasers. And that's the present limit of technology. And going further may be difficult because of thermal problem, for example, in the lenses. If you have a lot of power, you heat up. If you want to use it in a cryogenic environment, these lenses are kind of absorbing 10% of the power, and 10% of 100 watts is a lot. So you see that now we are going close with this kind of number to the present state of the art of laser technology. But of course, people will find tricks and probably can go further. Yes? So maybe you take this so that everybody can. This is not. Okay. Yeah.
Thank you. Maybe this is too naive, but why do we care about having such a big group of atoms when maybe we could be doing calculations in like smaller groups and then just like doing them faster?
So you mean smaller group and then connecting them in some way, or?
Just like what kind of computations, like computationally, how many atoms do I need? Like, do I need to move this many, like 12?
So to give the idea of number you need for quantum computation, you have to have in mind the number of physical qubits you need to have one logical qubit.
Yep.
And roughly the ratio is from 1 to 100, or 1 to 50, or 170 something. So it means that if you want hundreds of logical qubits, and you will see do nothing useful even if you have 100 logical qubits, you need 10,000 physical qubits. So there is not only a rush there, but a rush to imagine how to eventually connect several ensemble of atoms, which is also another very strong technological challenge.
I see. Thank
you. So people clearly for quantum computing are interested in having not 10,000, but they would be happy to have 1 million qubits. Okay. But probably the laser you need for that does not exist.
Okay, thank you.
Other questions? Yeah.
I have a question about the imaging of the.
Yeah.
After you do the first trap, they image the system, and then they repair the lattice.
Yeah.
How they do this image in a non-destructive way? Like the traps are deep enough to handle the photon kick? Or?
Yes, I think. Okay, I think I skipped that, and indeed it was the pointer. So I think the information is there. So when you do the trap, so you have a radiated laser which produces a downward light shift of the ground state, which creates the potential trap. And here is the expression of the potential, which is calculated by second-order perturbation theory. And then, indeed, you do the imaging using just the cooling laser. So you do it not in the mode regime, because you don't want to have this gradient of magnetic field, and you don't want to lose the atoms. And the best way to lose the atom is to have, at the same time, efficient cooling with respect to heating due to scattering of photon. So you go into the molas regime, and then you adjust either the detuning of the intensity of your molas so that you minimize the losses by scattering, which produce some heating. And basically, when you vary the detuning of your cooling laser, then the atoms become colder and colder, so you keep them better in the trap. But at some point, the scattering becomes so low that you don't have enough photon on your camera. And there is a trade-off, a choice of detuning. And typically, there is a detuning where you can scatter hundreds of photons. Typically, in our experiments, we scatter 200 photons without losing the atom. So this is easily optimized, but if you are not careful, you lose 10% of your atom during imaging. So I think the best performance, again, when you really optimize the thing, is a fidelity, measurement fidelity in the range of 10 to the minus 3 for the imaging and for the loss per image. So, which means that already, if you have 1,000 atoms in an array, you lose one by the imaging. But eventually, you can go further, because up to now, people are not manipulating 1,000 atoms. Okay? So here, that's what I missed. Here is the kind of image you see with your camera, where you have single atoms. So here, magnification was set so that basically most of the photons were impinging on a single pixel. And if you sum the number of photoelectrons impinging of a few neighboring pixels here, you get this kind of telegraphic signal as a function of time. If you take a lot of images, this is second time scale, so it is very slow, and you can have a lot of pictures there. And you have really a clear difference between 0 atom and 1 atom, and you see that the number, the fluorescence type is quantized, related to the fact that you have either 0 or 1 atom, and you see that there is never the fluorescence corresponding to 2 atoms. Okay? And indeed, in this first experiment, there is a very sophisticated high numerical aperture, which was specially designed, objective, which was specially designed by Institut d'Optique for this experience. Indeed, the Institut d'Optique is an engineering school about optics, so they were experts at that time about constructing light lenses. Indeed, now we can do more or less as a similar job, as good as that, in terms of field of view and things like that, just by using one single aspherical lens with compensation of aberration. And this works very well. Okay, so other questions? Yeah.
When you're performing this kind of experiment using SLM, I imagine these devices induce some kind of errors or noises. I don't know if they are negligible or how you deal with them.
Okay, so the imperfection of the SLM. I have another slide. I can show you this after the lecture. But typically, you have two kinds of imperfection. The different spots may have different intensities. And this you can control by a kind of feedback loop. You generate some array with a camera and with a good lens, you look at the array, you measure the intensity of individual spots, and you put some feedback on the modulus of these coefficients. And then you get very nicely uniform spot. And then it appears that the residual parasitical spots, which forms more or less a speckle, are much weaker, and they are never deep enough so that you load the atom there. So you don't care, basically, about them. Expect that if you look into the details, if you have a Gaussian spot like this, and if you have speckle around, if you are unlucky, you have a grain of speckle which may overlap with this, and this is all diffraction limited, so typically all this is 1 micrometer. Then you have some interference, and this produces a little bit of spatial shift of this, and this introduces noise in the position. So the position you get is not exactly what you program within 100 nanometer, but again, you can operate feedback loop, looking where it is, and if it's shifted, you correct a little bit the K, and this converges as well. So I think you can really do the thing really very, very perfect with the SLM. But it's some work. It looks like simple. Said like this, we spend weeks or more than that to really achieve very nicely with a very well-controlled separation between SLM, between spot.
Thank you.
Okay. Another question, maybe a last one before I continue. Yeah? No? Okay? Okay, so I'll continue. Okay, so here, so that's all what I would like to say about tweezer, about ground state atoms. I think we could further develop the thing by explaining the way people now can continuously load the large arrays by continuously having the mod coupled to some region where you store the atoms which are ready to replace the missing one very fast, but I think I will stop there for the tweezer setup. So now the second partner of this experiment, the Rydberg atoms. So I already told you about Rydberg atoms, but I focused on the circular one, and I like to start with historical things because I think historical context is always interesting. So when starts the physics of Rydberg atoms, 1985, so well before quantum mechanics, Rydberg, people were measuring spectra, observing spectral lines, and looking at the spectral line converging with some ionization limit. Rydberg introduced the famous formula that the binding energy is given by some constant, named the Rydberg constant, divided by the square of an integer, which is now called the principal quantum number. So it's well before, it was kind of empirical law, well before Bohr atom model and well before quantum mechanics. So then 1930, before quantum mechanics, Bohr explains with a kind of empirical model that this formula can be deduced from kind of quantum law, more precisely for the quantization of the momentum around the atoms. And the physical picture is that the electron is like a wave orbiting around the atoms, and that you should have a kind of standing wave for this matter wave around the atom. And so along one orbit, you should have an integer multiple of wavelengths. And this leads to the quantization law of the Bohr atom that you all know. Then I think maybe not so much known step in the story is the 30s, where Fermi indeed introduced a concept which is now extensively used in cold atom experiments, but also in neutron or nuclear physics experiment, the scattering lens characterizing a collision between quantum particles. And indeed, he used this in order to explain the shift of alkali atom Rydberg lines when the atoms were placed in the buffer gas. And indeed, the idea is that the effect is due to the interaction between the Rydberg electron with the electrons of the gas, and then introduce a scattering length for collision between electrons, which become a very important concept for the rest of physics. And then in 1955, Rydberg atoms with huge principal quantum number were detected in the interstellar medium by their microwave emission. And I like to mention this because nature and astrophysics is better than the lab for preparing Rydberg atom with very large quantum number. I think now the record, maybe it's even better, is not 100, but like 400 as principal quantum number. And up to now, we had no chance to reach such excited levels in the lab because the distance between two Rydberg levels in energy is very small, and the smallest residual electric field in the experiment is enough just to scramble the thing, and you cannot observe the discrete level for n equal 40. But you can have them observed in astrophysics. Basically, they are prepared by recomputation of charged particle, and as the vacuum is very good, as the electric field is very low, you can get narrow lines in the interstellar media. Then, I think a game changer, of course, was in the 70s, the advent of tunable laser, the laser, dye lasers appeared at that time, and allow to very efficiently prepare selectively some Rydberg level to make a lot of spectroscopy of Rydberg level. And I would like very much to mention here one of the founding fathers of this field of Rydberg level, Dan Kleppner, who unfortunately passed away before the summer. So I think a lot of things we are doing is related to Dan Kleppner's work. So here is an example. It's a spectroscopy of lithium atom in the presence of electric field. And when the field becomes large enough so that you mix all the multiplicities, there are very interesting studies that you can develop around the topic of quantum chaos, because the system becomes chaotic, and by looking at the statistics of the level, you can investigate how chaos manifests in the quantum framework. So this is a famous work. Of course, I will not develop this further. So let's come back to a more basic description of the Rydberg level, which indeed I will focus here on the Rydberg level, not of hydrogen. Hydrogen is the blue scale of level like this, which is exactly varying like 1/2 as a binding energy. So in practice, hydrogen is very nice because, no, not in practice, in theory, hydrogen is very nice because hydrogen, you can calculate everything. You get exact expression of wave function, matrix elements, everything you want to calculate, you find in a table of spatial functions. So you can also numerically compute this spatial function. For alkali atom, the thing is a little bit different. If you look at the level which are very close to the ionization limits, they look like hydrogen, except that the position of energy level depends on the value of the L orbital momentum quantum number. And you see that instead of having levels degenerate in L as in hydrogen, you lift this degeneracy. And that's indeed, this degeneracy is a consequence of one symmetry of the Coulomb potential, scaling like 1/r. And if you are dealing with alkali atom, for the Rydberg electron, the core is not just a proton, but it's a charge plus, but with some given size, which means that when the electron penetrates in the electronic cloud of the core, then the potential becomes stronger than 1/r, and then you break the symmetry of the Coulomb potential. And as a result, you lift this degeneracy. And then you see the origin of this removal of degeneracy is the difference of penetrability between S, P, or D orbit with respect to the atomic core. You know that when you increase the angular momentum, the wave function is determined by some centrifugal potential, which makes the electron further away from the core. So it means that S orbitals are penetrating the core more than P, more than D, and so on. And so you expect a discrepancy between hydrogen and alkali atom, which is larger for S level as compared to L level. So this is well understood and is described phenomenologically, but this also can be done on the basis of theoretical argument. So you can take this kind of empirical formula as the right way to describe the energy level of alkali atom. So instead of having the Rydberg constant divided by n squared, you correct n by a so-called quantum defect, which tells you how to modify the energy level as a function of L. And for each value of L, you get a different value of the quantum defect. So if you go to rubidium to have an idea of the kind of number you have, typically the quantum defect characteristic of S level is 3 units, which means that if you consider the multiplicity, the hydrogenic multiplicity with n equal 50, which is there at the position of this black line, the 50S level is 3 multiplicity below. So it falls in between the n equal 46 and n equal 47 multiplicity. So this looks a little bit like messy, but it's like this. And once you do the quantum defect, you know exactly where the levels are. So the 50S here with this quantum defect of 3, and the 50P a little bit above with the quantum defect smaller, and the D and the F level are still a very little quantum defect. It's like 800 megahertz below the hydrogenic level. So it's nearly hydrogenic already. So this is important because you know the quantum defects are tabulated with correction scaling with n minus the quantum defect square. So with this formula, basically you predict the position of any Rydberg level of rubidium with an accuracy better than a megahertz. And that's enough for characterizing the interaction, for example, between Rydberg atoms. And so usually the quantum defect, you take it equal to 0, you neglect it for L equal 4. There are residual small values, so for high resolution experiment, you can take them into account. This is well known. So then, kind of resume of the property of the Rydberg atom. The energy is given by the principal quantum number and quantum defect. The dipole matrix element typically has the size of the atomic unit times the square of the principal quantum number, which is indeed the most important property of Rydberg levels for S. The dipole is huge. It's thousands times larger than for ground state atoms, which means that the electric dipole-dipole interaction between the Rydberg levels is huge as compared to what it is in the ground state atoms. It also means that they are very sensitive to electric and radio frequency fields. Indeed, there is a huge field developing presently in which people try to build electric field or radio frequency or microwave field detector based on experiments measuring the EIT of alkali atom in a cell, where one of the levels involved in the EIT process is a Rydberg level. So there are a lot of papers presently about the way to use Rydberg level are sensor for electric, static, or radio frequency field. So this leads to strong interaction. The second important characteristic I already discussed in my first lecture is the long lifetime. 100 microseconds for low angular momentum Rydberg level with principal quantum number about 50, and 10 to 30 milliseconds for the circular Rydberg atom at cryogenic temperature, which means that you have a good system for quantum simulation with strong coupling. We'll see that the coupling will be in the range of tens of megahertz, and at the scale of this lifetime, it's already a fast coupling, and you can do interesting quantum simulations. So here is just to give numbers. I will not tell this number, but here you have the scaling of the main parameter of the atom we are interested in, the size of the atom n square, the dipole same size, and you also find the size, the scaling factor of lifetime and the interaction, the van der Waals interaction, and the dipole-dipole interaction. But let me more focus on another important aspect of the Rydberg level, which is the response to a static electric field, which is not yet very much used in the experiments. In most experiments, people have the atom tweezer prepared in a glass cell, which is just empty, without electrode to apply electric field. So one limitation may be the lack of control of residual electric field. But now more and more experiments include in the setup some electrode to control the electric field. And you can see here the importance of controlling the electric field by looking at the way the spectrum of the Rydberg level with principal quantum number around 50 evolves as a function of electric field. So here the Hamiltonian is easily written. It's the product of dipole operator by the static electric field amplitude. And indeed, all this is well known because you know to calculate the matrix elements for any kind of atom. For hydrogen, it's analytic. And for alkali atoms, indeed, you have to deal with the numerical calculation for low angular momentum level, but it works very well. As soon as you know the quantum defect, there is a way to calculate the energy. So then I think it's important to make a distinction between the level which are far away from the multiplicity, so the one for which the quantum defect is significant, and the one which basically are hydrogen-like and which leads to this energy structure which opens very symmetrically. Indeed, the isolated level are coupled by electric dipole field to the levels which are non-degenerate with it, and which leads to a quadratic Stark effect. And the general rule is that all the levels goes down, so Stark coefficient most of the time is negative, and it's stronger for when the angular momentum L becomes larger. Then, see if you have large enough orbital quantum number L, typically larger than 4, you neglect the quantum defect, all the levels are degenerate, and when you apply electric field to degenerate level, you rediagonalize the dipole Hamiltonian, and this leads to linear Stark effect. So these lines are really representing this linear Stark effect, and indeed, it's easy to calculate this from the first principle nearly. So in most of the quantum simulation experiments up to now were performed close to zero electric field. Sometimes a little bit of electric field is applied, and always with either S, P, and D level. And one reason for that is that people use a 2-photon excitation from the ground state, and with 2-photon excitation, the conservation of angular momentums tells you that you can access only SP or D level, depending on the polarization of your laser. But you see that there is also another huge space around there, where I can just depict by this horizontal line the circular level I talked about in my first lecture. And these are levels which are nicely manipulated, provided you set up a quantization axis. I explained you that to prepare, but not only to prepare, also to maintain pure circular level, it's necessary to always apply electric field. But then we have another nice property of circular level, it's that their position is nearly insensitive to the value of electric field. They have a little bit of quadratic Stark effect, but much less than the low angular momentum level there, which means that if you look circular to circular transition, it has a very long coherence time. It's much less sensitive to electric field fluctuation as compared to any other Rydberg transition. So that's the red thing is the field in which the present quantum simulation experiments are developed. The purple one is the field in which we try to develop our simulator using the circular atom with hopefully the advantage of having a much longer lifetime for performing quantum simulation on longer time scale. But I will come back to this at the end of the next lecture. So we have the two partners of the system, single atom, Rydberg atoms. Now let me introduce the interaction between the Rydberg atoms. So interaction is dipole-dipole interaction. So I consider two atoms separated by this vector R. R1 and R2 is the position of the valence electron in each of these two atoms, which are supposed to be alkali atoms. And then you have the well-known expression of the dipole-dipole interaction. Indeed, the product of the charge with R1 and charge with R2 is nothing else than the dipole operator corresponding to electron 1 or electron 2. So then, with this Hamiltonian, it's important to distinguish two different regimes that you can control experimentally. You can switch to one to the other by tuning some parameter. So the first regime is the regime where you consider all the atoms in the same Rydberg level. Let's say all the atoms in the 50s level. Then you have no matrix elements between 60s and itself. Because, for example, the parity argument tells you that the dipole operator is an odd operator, and if you take the average value on an odd operator of any wave function, it gives you 0. So there is no first-order interaction between these two levels, but of course they are coupled by dipole operator to p levels, above or below, and then as a result of second-order perturbation theory, you expect a shift of the two-atom level 60s by some coefficient called traditionally C6, which varies as 1 over R6, and this is called the van der Waals regime, and this corresponds to the van der Waals interaction. So for pair states where the van der Waals energy is positive, the interaction is repulsive, and the Rydberg atom will not like to collide. There are pair levels for which the van der Waals interaction may be attractive, and then the atoms may collide, and this may cause losses in the system, but we'll not be interested in that slot process. So the second interesting regime is that where the two atoms are in different Rydberg states, which I assume are coupled with the dipole, which have a non-zero dipole matrix element. So here I consider a pair of level where one of the Rydberg atoms is in S state and the other in a P state, with eventually different principal quantum number and an n prime. Then I have two levels with the same energy, which correspond just to exchanging the wave function. Then I choose the level so that dipole matrix element is non-zero, and then it results that there is a first-order matrix element of the dipole Hamiltonian there, which produces a splitting between these two states, and the eigenvector becomes symmetric and antisymmetric superposition of these two levels. So I think that's very well-known consequence of coupling between two-level systems. So the levels are written here. And the important difference with the van der Waals regime is that now the splitting, the energy shifts, are not anymore proportional to R6, but are 1 over R3, which means that this interaction is longer range as compared to the van der Waals interaction. So what about the calculation of C6 and C3 coefficients? Indeed, you can calculate them, maybe I mentioned this slide first, very easily, either by taking the formula you find in the book, but now we are lazy, we don't look at book, we look at the web. We go to this platform where you have some Python library, either a platform pair interaction or the platform ARC, and basically all quantum defects are built in, all matrix elements of dipole are built in, and you can ask the program to calculate you the energy shift as a function of distance, gives you the parameter fit of the variation of this as a function of F1 over R3 or 1 over R6. So if you are lazy, you have even a graphic interface that you can use. Of course, you have much more feature if you use the Python package, and I encourage you to look at the Python package of this if you need to know anything about Rydberg atoms. So what is the magnitude typical of this interaction, van der Waals or dipole-dipole? Well, here I have represented as a function of distance the energy shift due to interaction for different kind of interacting levels. So at the top, I put the strength of the Coulomb interaction between two rubidium ions, basically the repulsion between two positive charges. So it's there. So this magnitude corresponds, is an energy shift in Hertz, so like 10 to the 11 Hertz at a distance of 1 micrometer. And then at the opposite here, I put the interaction strength, dipole-dipole interaction for two atoms in the ground state. I already mentioned the van der Waals interaction between two atoms in S states when discussing the collisional blockade. So the magnitude is like 16 order of magnitude below the interaction between the ions. So this is really a weak interaction, the van der Waals interaction, if the distance is in the range of several micrometers. So in between, you have what is of interest for us, the red curve, which is the typical interaction between two atoms with principal quantum number 100. So it's a little bit more than what is used in the experiments. It's rather 50, 80, but it gives the order of magnitude and the shape of the curve. And so you see that we are much closer to the ion pair than to the ground state of the atom, and that's due to the huge size of the dipole of the Rydberg atom, which is not as strong as a charge, but not so far away. Here there is less than 1 order of magnitude in between. So another feature is that at large distance, indeed, typically the interaction becomes van der Waals interaction for two atoms in the same state, but it switches at some distance, typically 10 micrometer, to 1/3 dipole-dipole regime, which corresponds to the distance at which the dipole-dipole first-order matrix elements becomes of the order of the energy difference between the Rydberg level. So at short distance, everybody looks like 1/R3. At large distance, it's rather 1/R6 if you have 2 times the same level, but still 1/R3 if it's different Rydberg level. And you see that if you compare also to the magnetic dipole-dipole interaction, which is also very famous in the ultra-cold atom experiment where people are studying dipolar gases. So all the properties of dipolar gases are built on interactions, magnetic interaction, which are like 12 orders of magnitude weaker than the dipole-dipole interaction between Rydberg level. So it's really a different physical situation, even if you can consider that we are studying the physics of a dipolar gas. It's not a gas, it's single particles, and the distance between particles is not a fraction. It's not counted in nanometers or tens of nanometers, but in tens of micrometers. And we have even at this distance much larger coupling. So that's it. Let's say a word about what happened if you put the atom too close. Here, I was kind of optimistic going to 1 micrometer, because indeed, well before the situation becomes very messy. Here is the calculation of all levels which may interact if you choose only a very small part of the spectrum. And here I have levels ranging from 77S level to like 66D level. And you see that except up to this distance of about 4 or 5 micrometers, if you have shorter distance, you have a kind of spaghetti of levels with a lot of anti-crossing. And that's a reason why I think the physics of Rydberg atom developed very much as soon as people were able to prepare the Rydberg atom in optical tweezers. Because without the optical tweezer, even with a very dilute gas of Rydberg atom, as soon as you have one atom every few micrometers, so a lot of them will just be attracted, collide, create charges, create a plasma, and then the physics of Rydberg atom stops, and you start the physics of cold plasma, which is a completely different physics. But the idea to prevent the atom to collapse to each other by having tweezer is making the Rydberg atom physics much more under control, and that's the heart, I think, of the development of these experiments about quantum simulation with Rydberg atoms. So I think my plan was then to start about experimental characterization of this general feature of the Rydberg atoms, but as I am running out of time, I will stop here and we'll discuss about the experiment in the next lecture. And thank you for attention.
Thank you, Professor, for your lecture. With regards to the use of circular Rydberg atoms, I was a bit confused about the technical challenges of using them to quantum simulations, because usually when you deal with cavity QED, it's like the golden standard, right? To use like the circular states. So what are the main challenges that you face when you try to use them for quantum simulations?
The challenge is that everything is more difficult, but there is a reward. You win a factor 100 over the time scale. And so I will detail about the challenge, because the last part of my lecture tomorrow, I will talk about the way we try to build this quantum simulator. So I will give you much more details about that. It's of course more difficult to prepare the circular atoms as compared to the low angular momentum. Laser pulse is not enough. It's more difficult to detect them because basically for detecting the low angular momentum Rydberg level, you just look whether the ground state atom disappears. And if you know that your preparation is perfect, you know that an atom which disappears corresponds to one atom in a Rydberg level. So if this Rydberg level is the one which is resonant with the laser, there is no ambiguity. If it is going to the Rydberg circular level with complex way, there is a lot of mistake in the measurement. So measurement is more challenge. And another challenge is related to the fact that circular atoms have no optical transition, which means that it's difficult to address them individually optically. But there are tricks to overcome that. I will tell you about these tricks in the last lecture.
Thank you.
Other questions?
Thank you for your lecture. It's also about circular levels. I was thinking why these circular levels are like not perturbed by electric fields, because it's always said that Rydberg atoms are very sensitive to electric fields. But what happens with the wave function, or what's happening?
So what happened is that so there are both mathematical argument and a physical argument. So the mathematical argument is that if you calculate the Stark effect for hydrogen atoms, so you had exact calculation, you find that the parabolic basic is the right basis, the circular state belongs to this basic, and the first order Stark effect is strictly zero. Second order Stark effect is also zero, except if you include interaction with other multiplicity, which means that the level which are there and there are repelling the circular level, but you see that it's very symmetric, so there are levels upwards which are pushing the circular level downwards, and these are pushing it upwards, so the residual quadratic Stark effect is a differential effect, which is smaller than any number you find for the quadratic Stark effect for low angular momentum. And the reason here is that here, these levels are placed in between, but never exactly in between, which means that this is close to that, and this is pushing it down more. Then you have also to calculate the matrix elements. But at the end of the day, the Stark effect of the circular level is several orders of magnitude smaller than for this. It does not mean that it is completely negligible, but okay, given some precision of the residual electric field, circular level is always a better choice. So for having long-term coherence, this is favorable. Okay.
Okay, thank you.
Other question?
Hi. Yeah. When you show us the trap that for ions that doesn't use the spatial light modulators with different frequencies, how they manage to compensate this frequency noise of the traps?
To compensate?
The different frequencies of the traps, because they use different frequencies to...
So you mean with the AOD strategy?
Yes.
So here, each trap corresponds to one frequency sent to the AOD, and you can buy, indeed, very good synthesizer, which are rather arbitrary waveform generator, when you program a sum of sine function with the different frequencies. And it gives you a spectrum with narrow peaks, and each narrow peak in the spectrum produces a single trap there. So maybe I did not get your question.
But every trap would have a different frequency, so when you can control the intensity.
So the frequency of the trap, you should not confuse the frequency of the field used to generate the trap with the frequency of the trap, which I would say is the oscillation frequency inside the trap. So indeed, each trap is generated by a beam with a slightly different frequency as compared to the other, but the frequency difference in the range of like 10, 20 megahertz, and it does not impact at all the trapping potential because the detuning for trapping light is tens of nanometers. Okay. So 10 megahertz is completely negligible. And you can even compensate this by changing the power of individual trap, but you don't even need. For having identical trap, it's more important to compensate for the efficiency of the AOD, which is less if you go far away, but you put more radio frequency power on this sideband, and it's okay.
Thank you.
A last question? No? So let's thank Michel again.
Thank you. So this battery should be...
So this is yours, though?
No, this is not mine.